So hey guys, welcome to the channel CodeChef. If you want to learn competitive programming and get a good hold on DSA, this channel brings you the exclusive content on these things, right? So you can watch video editorials for CodeChef contest problem as well as you can learn new skills on DSA on this channel. So if you are new to the channel, then do subscribe the channel and turn on the bell notification. Myself Chirayu Jain, I'm a CodeChef educator, and in this video we are going to learn about Dijkstra's algorithm code in the series of shortest path algorithms. Okay guys, so now let us begin an understanding on the code for the Dijkstra's algorithm. So we have seen the theory part of Dijkstra's algorithm, we have seen what parameters are used, why basically the Dijkstra's algorithm is used to calculate the shortest distance from any source to any other vertex, right? So now let us see how we can implement this Dijkstra's algorithm quickly. So here we are taking initially three things, that is the number of vertices that we have, the edges that we have, and the source vertex, right? So we can take source by convention as 0, but it not necessarily in every possible case, right? So we can take the dynamic source as well, like any vertex we can take as a source and we can formulate what are the distances, the minimum distances to the other vertex from this corresponding vertex, right? Now the second thing is that we'll maintain an adjacency list, right? During the construction of the graph also we have seen that why do we require an adjacency list to make it clear and approachable, right? So if you have not watched that how we can initialize the graph, what is the graph structure, so you can watch the graph series present on this channel as well, right? So here we have taken the adjacency list to construct the graph, and also we are taking the distance array, right? So we have seen the three important parameters that are used to understand the Dijkstra's algorithm, namely distance, the nodes which we are traveling, and whether it is visited or not, right? So we are taking this distance vector, right, to calculate that okay, this is the current distance or the weight, the approachable weight from the vertex that we have as of now, right? So what we will do, we'll initialize it with int max initially, right? We have seen that we'll initialize it with some infinite value, right? So we have initialized it with int max over here, and we know that whatever source we are considering, we'll mark that distance as 0, because from that source we'll consider all the other source, all the other nodes, right? All the other vertices we'll consider from that particular source. So the distance of that source will mark as 0, right? We have seen that in the explanation. Now simply we'll input the starting and the ending vertex and the weight corresponding to that edge, right? So we'll input that and we'll make the graph structure of it, right? We'll enter that into the adjacency list, right? Since it is an undirected graph, so we'll mark for both v1 to v2 and from v2 to v1 with the corresponding weight, right? Now the portion, right? The thing is that at each iteration in the theory part, we have seen that we are taking the vertex which has the minimum weight, right? So if we are trying to get the vertex with the minimum weight, in order of n time we can loop around all the nodes and get the minimum weight vertex out of it, right? So that will cost us the number of nodes that we have in the linear time complexity. But can there be a better possible way to get the minimum out from a set of nodes, right? Yes, there is a possible way, that is using the priority queue. In priority queue we are using min heap, right? So at the top of the min heap we'll always get the minimum value, right? So what we'll do, we'll implement this priority queue and try to get the minimum distance node every time throughout the iteration, right? So that we are trying to use here, right? So to reduce our time complexity. So now what we do, initially we push whatever value we have, that is 0 for the source node, right? Because the distance is 0, we are considering for the source and the value of the source that we have taken, right? So we'll input that into this priority queue. Now the next steps, right? While the priority queue is not empty, why this condition? Because we are taking all the nodes which have been visited once, right? So we are taking whenever we are considering any particular node, we'll pop that out from that priority queue so that we'll not visit that part again, right? So this is here, right? So while priority queue is not empty, right, what we will do, first of all, we'll in the priority queue, what we are trying to store here is first the distance and the second one is the vertex, right? So the distance will take out from that is the first value in this pair, and the second one is the vertex value, right? That is the second value, and then we'll pop that out, we'll pop that particular node out, right? Now what we'll try to do, we'll try to explore all its neighbors as we are trying to do in the Dijkstra's algorithm. So we'll make that iterator and we'll start from this vertex, right? The vertex which we have popped out, we'll start to explore all its neighbors And in this, what we will do, this iterator, this adjacency list consists of two things, that is the node, right, and the weight corresponding to it, right, the distance between the edge between the two vertices, right. So the new vertex will come out as the first value, and the distance between that will come out the second value, right. And now what we will do, we'll see that if the distance on that particular vertex is greater than the combined sum of the edge value that we have, right, this edge value that we have plus the earlier distance that we have got, right, the earlier distance, the corresponding distance over that particular vertex, the previous vertex that we have got, if the sum of these two is less than the distance which is on this new vertex, then what we will do, we'll update that vertex, right. So how we can do this is distance of max will simply update with this corresponding value to that new vertex, right. And then this particular pair, right, this particular node pair will be pushed into this priority queue, so that we could get the minimum every time. So first what we will do, we'll make the pair and we'll add the distance first and then the vertex value, so that on the basis of this distance, right, we could get the minimum value every time, right. So this is the function of the priority queue, and at last what we will do, will output all the nodes and their corresponding weight from that particular source node, right. So this is typically the simple code for the Dijkstra's algorithm. So if you see here, I have already entered the test case for the example we have considered in the theory lesson. So now let's run this code for this and see what is the output that we are getting. Okay, so for the node 0 we are getting the weight as 0 that we have initialized, right. For the node 1 we are getting the weight as 2, for the node 2 we are getting the weight as 4, and for the node 3 we are getting the weight as 5. So this is what we have seen in the theoretical part as well. So as far as we look for the time complexity and the space complexity of this particular code, right, so the time complexity was polynomial, or we can say order of n square, when we have taken, if we have taken the consideration that we will get the minimum in order of n time, right. But if you see here, we are taking n nodes, and for each node we are traveling the number of edges, so that is order of n plus e, and the log n time complexity for getting the nodes out, right, from this priority queue, right. So if you look at the major objective, like in the, not in the depth, but if you look at the in terms of CP, or if you look at the more, you know, big overview of this particular time complexity, so you can say it as n log n, right. But we are considering the edges also, so order of e plus e will be the most appropriate term, but n log n would also suffice. Now if you look at the space complexity which we are using, right, so in spite of using this, you know, adjacency list, we are obviously using all the graphs will get as input, but also we are using the extra space for this distance max array to get the distance, and also we are trying to get the space for this priority queue, right, that is order of n. So basically for these two we are getting the order of n space complexity. So we have discussed about the time and the space complexity and the overall approach of the Dijkstra's algorithm.